be behind the podium, and I think my technology is working now since we got a new battery. So I guess that was last week's topic, right? Batteries, maybe? So it helps to have fresh ones when you need them. So if I get too far from the mic and you can't hear me, wave your hand or something and let me know, and I will come back this way. But I hate being shackled behind the podium. A couple of thank yous in advance. We have our master teacher, Miss Yolanda Kirkpatrick here. Stand up, please. Yolanda prepared lesson plans for teachers to take back for classroom activities. That it describes some of the activities we're going to do today, and then things that teachers can do with their students outside of this setting. So that was a great help to us. And she stayed with the research group and had weekly meetings with us. And she's the one that took all the research speak and kind of filtered it down to be age appropriate for this group at this learning level. So lots of thanks to Yolanda for that. We've got a whole bunch of people here from the group that I work in at ORNL, which is the Building Technologies Research and Integration Center. Most of them are back in the cafeteria right now getting their instruments ready for your hands-on activities. So I won't introduce all of them. We have one here with us, Dr. Roderick Jackson. Roderick, thank you. So Roderick deals a lot with home energy efficiency. So he will have a display and have some information about some home efficiency experimentation that we have done in the center over the last 3 or 4 years. So you can talk to Roderick about that. Also, Roderick is a Georgia Tech grad, so if any of you are thinking about Georgia Tech, you can. Yeah, you got it. You got something on there? Yeah, you got it? Yes. Oh yeah. Yeah. So pick his brain when you get a chance. So basically what we thought about months ago was the topic was going to be less energy in buildings, more dollars in your pocket. And I realize that may not mean a lot to some of you who aren't paying the electric bill or the gas bill this month. But this was a topic we came up with in September of last year, and we were going to do this in October, and things happened with the federal budget, and we got rescheduled to now. What we didn't know was that we were going to have an epically cold January. So it's really been in the news in the last 2 weeks that bills are going to be astronomically high when they come this month. I haven't gotten my gas bill yet, but I really don't want to see it when it comes. I know.
Bill I've ever had.
How much?
The highest electric bill I've ever had.
Yes. Was it double or triple?
Literally double what I've
Double.
ever paid. So,
Right.
Yeah.
Right.
Or Kingsport.
Electric or gas?
Electric.
Okay.
Yeah.
Okay. Here we're a little bit different in the East Tennessee or in the Valley area because about 57% of people heat their homes with electricity, and that can be credited to TVA and their initiatives with electric heat pumps. Nationally, most people actually use natural gas. About 57% nationally use natural gas, and then there's other fuels in there. But certainly people in the Midwest are suffering. Those that use LP, that don't have access to natural gas, we've heard about shortages. Prices on the spot market are a lot higher. They always are this time of year. So definitely dollars in pocket is going to mean something to people for the next month or so. Then we're going to go into swing season, and everybody's going to forget about it until July or August. And then we get that cycle for cooling season again. But efficiency definitely can help keep money in your pocket for other more fun things than the electric bill. So stepping back, this is East Tennessee in 1933. This is from the Norris Dam area before Norris Dam was impounded. And I wanted to show this because we tend to forget that it hasn't been that long since we did not have electricity readily available in this part of the country. In fact, most of rural America did not have easy access to electricity. They either didn't have access or they didn't have the money to connect to the electric utility there. So TVA came along here in the Valley, and also nationally the Rural Electrification Project was brought out about that same time. And people like these, I believe this is Miss Harriet Hankins and her family, were able to get access to electricity. They brought the lines out, and they also had financial assistance to help people that were just getting electricity purchase their first convenience appliances like refrigerators, because they literally did not have the funds to buy those modern conveniences that we take for granted now. So, we assume that this is all great and wonderful. We all have electricity and we probably use too much of it and we use it frivolously. We have that in the US, but the reality is in the global market, and particularly emerging countries, they don't have ready access to electricity. In particular, an example is India, where there's about 400 million people that don't have access to electricity. That's a lot of people. And their economy is growing. They're getting access to more technology. They're manufacturing. Their standard of living is rising. They want access to electricity. They have to produce it and distribute it is a problem. And that's an issue globally because there's still more and more demand for energy globally. And global demand will eventually affect our situation here as certain resources are priced on a global market instead of just on a US market. But in India in particular, one of the big challenges is as these folks get access to electricity for the first time, one of the things they want, well, there's two big things they want. They want refrigeration. They would like to have refrigerators in their homes for food keeping. And the other thing they would really like to have is air conditioning, which we all take for granted. We air condition our whole homes. We air condition rooms we don't use, that we're not in. They just want to get a room air conditioner. And there is a huge millions that want that technology, which we consider, low key, something you could go buy at a big box retailer for under $100. That's a big item for them, and it's going to drive a huge energy demand in that country and other emerging countries, such as those in Africa. So we may have come past this point from 1933, but a whole lot of the world has not, and they have a need for energy that's going to grow over time. So for us in the US, we know that our buildings use about 41% of total energy in all forms. We actually, about 73% of total electricity is used by buildings. And that accounts for about 40% of CO2 emissions, 13% of water consumption, about 40% of natural gas consumption in the US is strictly for buildings. That's for conditioning our buildings, keeping them comfortable the way we like them, and for keeping the lights on, for powering our receptacles, for all our miscellaneous loads, all those modern conveniences. This particular photo, I believe, is of the TVA plant in Gallatin, Tennessee. And it's really interesting. We tend to get more and more efficient, and as we get more efficient, we seem to replace those loads with gadgets that we like. And there's an interesting study out of how many people in this room have access to a tablet or an iPad on a daily basis. Okay, most everybody. There's a study that was put out by the Electric Power Research Institute about 2.5, 3 years ago, where they were studying just the impact of the iPad on electric demand globally. And they had some projections. And basically, in 2010, it was showing that 250 megawatt power plants were needed, and they needed to run at half power to power the iPads that were out in circulation at that time. This is 2010. And they had some projections about what if iPad sales double? What if they triple? At that time, there were only 68 million iPads out there in circulation. The last numbers that I saw from Apple, which I believe were released in October, was 170 million were already out there.
That's just iPads?
Just iPads. That doesn't account for all the other kinds of tablets that we have available, or the newer phones that are kind of a cross between a phone and a tablet, those mid-size phones. So we get more efficient with some things in our buildings, and we just find other places to use the energy. So that's a continuing challenge, and if you want to look up, there's a topic that's some controversy called Jevons paradox. Some of you may have heard of that. You can read about that. Basically, talks about that whatever you gain in efficiency, you're going to spend it on something else anyway. So kind of a depressing thought. So how do we use our building energy now? And the reason I show this slide is because the group that I work with, and Roderick, who I've lost Roderick, Roderick works with us. We focus on several of these areas. Some of the other national labs hone in on other topics. For example, Lawrence Berkeley hones in on lighting. The group that I work with, we do a lot of work in heating and cooling. Heating, cooling, and ventilation. 38% of power, roughly, for your building, typical building. It varies depending on what part of the country you're in. Is it an industrial building? Is it a house? That kind of thing. But we'll just say round up 40% just to heat and cool your building. And a lot of that gets wasted, a lot of that. We also work in refrigeration, which in your home just means your refrigerator or your freezer, It also means supermarket refrigeration, industrial refrigeration, all those distribution warehouses that have to get your frozen pizzas to you, those places. We talk about wet cleaning or laundry. That's a small part, but that encompasses also the dryer part. And the dryer actually has a huge impact on your house. Your dryer can totally evacuate the air in your house or turn it over in less than an hour. So all that energy that you spent to get that temperature just the way you like it, it just went out through the dryer. So there's a big initiative right now on improving dryers. Lighting, we don't do lighting at Oak Ridge National Laboratory, the group that I work in. They do a lot of that at Berkeley. And then other is all the goodies that you plug in. Could be your cooking, could be your iPad, your computer, any kind of miscellaneous, your DVR on your television, all those good things. So this is like the one really hard science slide that I have in here. The rest aren't so painful. So I assume that most everybody in here has had some basic heat transfer concepts. So this is how that applies to a house. The same is true for any kind of a building such as this or an industrial building. So you have the three modes of heat transfer. You have convection, conduction, and radiation. Some of the hands-on experiments that you're going to see later today are going to really focus on radiation and, to some sense, convection. You'll see that. I don't think we have any conduction activities today. This slide kind of oversimplifies what's going on in your building, though, because this is showing the natural effects from the outdoors on what happens to your building. This is not showing any of the internal loads. So when we have the outdoors to deal with, we also have internal loads, which is people, lighting, and all that equipment, which basically when you turn it on, all that power that you're using goes to heat energy. And your cooling system has got to pull that heat out and get rid of it to keep your space comfortable. So all that's got to be accounted for. And these are the items that drive your air conditioning bill. And right now in East Tennessee for the last month, it's been the cold weather. You know, maybe in July, August, we'll see the radiation. It'll be solar heat gain to the building during the day that's going to drive it. So one of the things that we look at a lot in our group has to do with how the building picks up heat transfer through radiation, through the sun's rays. We do a lot of work on materials and how those materials reflect or absorb that heat, how the temperature of the building then is radiated back out into the space outward. So we're going to have one hands-on activity that's going to let you look at different reflectivities of materials. Because in the summer here in the South, we want to reflect as much as we can so that we're not gaining that heat into our building. I didn't look on Google to see which kind of roof this particular building had. I would be willing to bet it's still got a black surface roof. The white cool roof movement really took off about 15 years ago in my experience. Either way, if you go up on the roof of an industrial building, it's going to be hot. But a black roof building very often can be about 85 degrees warmer than the ambient temperature. So on an 85-degree day here, you get about 170 on the surface of the roof. It's quite unpleasant if you have to go up and check on mechanical equipment and things like that. A white roof may only vary by about 10 to 15 degrees, but you may get a sunburn. So this is a nice slide for homeowners that the EPA has put out as part of their Energy Star program. And I show this because one of the big drivers in that 40% heating and cooling energy load is air leakage. We have all this great conditioned air in our building and we just let it go out the cracks. Through the doors where we didn't seal like we should have, or in my house where the cats come and they claw at the door and pull all the sealing out. It goes out through the vents, it goes into our attics, which we don't condition. We have ductwork in our attics. We run all our cool air in our ductwork through the attic and it leaks out there. Ceiling lights, lots of opportunities to improve upon. And modern codes and building practices are starting to pick up on this and correct this. The problem is after the building is built, a lot of these things still have to be maintained. And we as homeowners tend to not be very good about maintaining things. And we let things decay into such a state that then we need a whole home energy retrofit and a study, and we need to pay somebody to come in and fix all of our problems that we just let happen over time. And It definitely goes on in my house. I don't have time to deal with a lot of this stuff, so I can't hold my own house up as a standard for good practice because I'm just like everybody else, and I think most of my coworkers are much the same. So what do we do in the Building Technology Center? We've got 3 main areas that work on buildings. We have a 4th group that does ancillary activities for federal buildings. You're going to talk to people today in the envelope group and that work with equipment and integration. So on the envelope side, they're looking at the materials. They're looking at reflectivity, emissivity, they're looking at durability, they're looking at moisture. That's a big thing now. Moisture durability, the ability to keep conditions outside where they belong or to move water across that membrane in the appropriate direction. I don't know if anybody here has a house that is made of EIFS, E-I-F-S. In East Tennessee, sometimes people call it EIFS. So it's an exterior insulation and finishing system. It's kind of a manufactured stucco system on a house. There were a whole lot of lawsuits about 10 to 15 years ago because of moisture problems with these systems. And it wasn't the material. Material was fine. It was the installation methods. And that's part of what I want to get across during this discussion is that we at the lab, we talk about materials a lot. We hold up materials as the solution, as the holy grail. It fixes a lot of things. In the buildings world, the material is not enough. You've got to get it so somebody will buy it and somebody can get it installed properly and hopefully someone will maintain it. But having the material alone is usually not enough to solve your problem in the long term. And what we talk about a lot at the lab is we talk about fixing problems with speed, scale, and sustainability. So we want to do it quickly across a very large scale market, and we want to sustain energy efficiency over the long term. Unfortunately, even some of the best materials and the best systems that we have, they do decay in their efficiency over time, just the natural aging of the product. On the equipment side, the equipment for us is mainly what keeps your building hot or cool. It takes care of that heating, ventilating, and air conditioning load. Heating, cooling, and ventilation. It also, we cover water heating for homes mainly, and refrigeration in the form of your refrigerator or also the supermarket refrigeration. So the idea is deliver the same amenities because none of us want to go backwards in time. None of us want to go back to 1933 and have to go chop wood to boil water to wash clothes or something like that. We expect the same level of amenities. We want to pay less for it when we go to a big box retailer, so that's another challenge. The government wants us to use less energy, and hopefully most people want to use less energy. Although when you go shopping, most people probably don't have energy on their mind unless it's right in front of their face, like a sticker that you see on a refrigerator, which now we have a way of comparing. Unfortunately, a lot of the things that we work on, you cannot intuitively look at things and just know if it's going to use less energy. Maybe you can if you've worked in the business a long time, but with a car, most people have a feeling of, will this truck use more energy than this small, compact, hybrid car? But on a house, not so much. And on a piece of equipment, not so much. So equipment people, part of the hard part there is delivering the product and making it palatable for people to want to spend a little extra money on to get that benefit. Then another group that we have looks at integrated performance of how all these things work together, because the funny thing about buildings is when you change one aspect of the building, it tends to have an impact on other areas, and sometimes you may not want that effect. So we tend to test equipment that has been developed or systems that have been developed that have not yet gone to market on test buildings and in test assemblies so that we can kind of get the bugs out before someone takes it to market. I'll show you an example of a product that was developed about 20 years ago, and it was great. It saved a lot of energy. It was a new company delivering this product, and they sold it for a while, and then they had some failures, and they had to have a recall, and the recall basically did the company end. It was the end of the business for them, and that technology languished for another 17 years or so before somebody else picked it up and actually was successful with it. So we try to help people avoid that failure mode and get a worthy product out to the public the first time around. So that speaks to the durability and reliability aspect. So science and application. So this is what ORNL is really known for, these 4 areas: neutrons, materials, computing, and manufacturing now. So we do a little bit, we have overlap in all of these areas. We have some people that are actually using neutron science to observe 2-phase flow in refrigeration equipment, such as what you have in your house. The idea there is to optimize refrigerant flow, heat exchanger usage through that visualization method. We also use high-performance computing to do energy modeling on buildings. We have a pretty nice tool online. It's called a Cool Roof Calculator. It's not really for your house, it's more for commercial buildings. But to the end user, it looks like they're putting in some numbers on a website and they're getting a calculation done. They're not. The calculations were already done on a supercomputer previously. You're just putting in information that tells the computer where to go in the database of completed calculations to give you an answer. So we have taken a lot of computing power and condensed it down to make it available to folks that are laypersons that would not be able to complete a really detailed calculation on their own, or they don't have the computing resources either. Another thing that we do is we look at how to manufacture things to improve them, such as heat exchangers is an example of one area where there's a lot of opportunity for improvement. Heat exchanger in your house, you have one on an indoor unit and one on an outdoor unit if you have a split system. If you have a package unit, those 2 heat exchangers are packaged in the same box outside. The animation there is a super hydrophobic material. The envelope people that you're going to talk to, they really like to look at ways to reject water, to keep water from getting into the building assembly, because it tends to destroy the materials. They tend to rot when water comes in. It also destroys the insulating effect of a lot of materials when you get water penetration. So that's an example of a next generation material that we would like to see incorporated into other kinds of building materials. So some of the things that we do are small scale. We do in little chambers that sit on top of tables. We look at material properties of small scale samples. We also take larger assemblies. Literally, we have technicians that build assemblies of test walls and test roofs, because there's 1,000 different ways to cover a building, a commercial building or a house, literally. And all of these assemblies have to be tested for heat transfer, among other things in the building world. We also have to consider things like fire and smoke. We don't do that, but those are extra issues that have to be dealt with for building assemblies. So we have chambers that are big enough that we can build 12 by 12 wall sections. And I believe the roof section, none of those guys are here right now. The roof assembly is bigger than 12 by 12, but we can build an entire roof as if it were over a house, and take it into a chamber and subject that to a heat source, which in this case, in the upper left, is heat lamps to simulate the sun's effect. And then we have a chamber down below that's monitoring the heat transfer through that roof into that attic cavity that we built specifically for that purpose. They also have a new chamber, the one on the bottom left. Dr. Deanna Hun, that's her research apparatus that she's doing work on quite a bit. And that one is novel in that we have the ability to simulate sun. We have the heat lamps, but we can also do wind-driven rain. Not at the same time as the heat lamps are on. That would not be good. But that's a new feature, to be able to force rain against the wall and see how that building material is going to perform. So all of these assemblies have hundreds of sensors embedded in the section of the wall or the roof, on the surface, on the underside, that are going to stream data back to a data collection system so that we can evaluate the performance and compare it to other historical tests that were done. So one of the things that they do, the slide that I showed earlier talked about radiation, and we looked at reflectance and emissivity. So one of the things they do is they look at how does that material behave over the long term. And unfortunately, they all tend to decay, they get old, and in the case of roofs, we tend to get a lot of dust, just get carried by the wind, It accumulates on there. We also end up getting microbial activity on that surface. So we have the ability to test this. We have some samples where we can deposit dust and microbes in a suitable density on a sample and then evaluate that. And this is a big deal for manufacturers because we work with techniques where we do accelerated aging tests. So we figured out ways to look at something over maybe an 18-month period and project how it will perform over the 7 to 20-year lifespan that you might expect for that roof. But we did it in 18 months, so we can get that information to the manufacturers and they can go ahead and maybe refine their product and get it out there on the market. They don't have to test their product for 7 to 20 years. That's a big help when we're looking at new ways to improve assemblies, such as spraying on cool roof products instead of building it in the first time around. The retrofit market is huge for that particular application. So the envelope folks, one of the things that they look at is what can we do with our materials that might take care of some of the variations that we get in the field with assembly, because not everybody has the same skill set level or the same training. And also, I don't have a slide of this, but we also have to deal with tremendously varying climate conditions in the U.S. If you look at a map of the U.S., we've got Miami, Florida. It's probably in the 80s there today. I was in Orlando this week and it was 85. And you know, here it's going to be in the 20s tonight, I think, snowing elsewhere. Then we have desert U.S. conditions, things like that. These particular examples were humid type climate failures. But this is the kind of thing that ends up in class action lawsuits against manufacturers if they haven't figured out how to prevent installation type activities, or if they haven't figured out recommendations to give contractors and owners on don't install this product in this climate. So this is not what you want to have on your house or your building. The bad thing about envelope failures in particular is it's very, very expensive to fix after the fact. Equipment is a lot easier to change out. Envelope is extremely costly. So on the equipment side, some of these things you might have a heat pump water heater in your house right now. That came on the market in force about 3 years ago, and that's something that took about 20 years to get to market. That was that failure item that I mentioned. Somebody built it and got it to work, and then they had a problem and had a recall. So now there was one manufacturer that stepped up and really pushed this technology, working with ORNL, and brought this technology to market. And they first manufactured it in China, but they were able to bring their manufacturing process back to the US, and they build them in Louisville, Kentucky now. So it's a manufacturing success. The other thing is this whole thing about speed and scale. The scale is really important on this particular piece of technology because 2 or 3 other manufacturers have picked up on this now, and there's a competitive marketplace now. There are several manufacturers that offer these items. You can get them all at a big box retailer. You don't have to go to a specialty plumbing supply place. And this is a really big efficiency improvement over conventional electric water heating devices. And this will become the standard really for electric water heating in the future. Another thing we're working on is the window AC equipment, which is a really humble piece of equipment. This is not an exciting piece of equipment for anyone, probably, unless you're selling it. It's not rocket science, but there are 50 million of them in the United States. So there's a lot of people that are buying these things. They might want to upgrade to something else in the future, but then again, these kinds of pieces of equipment lend themselves well to small places that maybe aren't attached to your house, maybe a room in a garage, in a detached garage, or something like that. And also, this is really the first accessible piece of cooling equipment for the emerging markets, or for those that are financially challenged they can't get enough funds to put in a whole house system. Which, by the way, we in the U.S., we use forced air to deliver air conditioning and cooling and heating to our houses and other places. In Europe, it's really more water-based systems, and in Asia, it's refrigerant-based systems. So don't assume that the house system that you have is the universal system in the whole world, because it's not. In fact, in Asia, distributed refrigeration systems are the norm. So kind of like that window AC unit, but flat units that hang on the wall, and you might have several of them in a home. The advantage of that is they can control cooling to only the rooms that they're occupying at that particular moment, so they save energy that way. Another thing that we do a lot of work in is ground source heat pumps, which certainly you can buy those for your house right now. They are more expensive because you have to put in a well field to provide the heat source or the sink for the cooling. The one on the left I brought for this because this was something we worked on. It's a gas engine driven heat pump. So we're using a gas combustion engine, natural gas driven engine, to drive a heat pump. And this was really brought about because there was a need in Las Vegas for an alternative to electricity-based cooling. Back before the recession started, Las Vegas was booming. So many people were moving in there, they couldn't keep up with the electric demand. It was the place to be. It also happens to be really hot there. They need a lot of cooling. And there was just not enough electric power to meet that demand. They are pretty far from powered plants, and adding distribution was going to take a long time. It would be extremely costly. So this product is available in a different form in Asia and was kind of redeveloped for the US market as an equivalent replacement for a conventional rooftop unit that you might see on a strip mall or a big box retailer. And it really only needs a trivial amount of electricity. It needs electricity for the controls and electricity to run the condenser fan and the fan that moves the air around your space. But the cooling system is entirely powered through that natural gas engine. They had plenty of natural gas piping available. So it made a lot of sense for them. It met their need. Unfortunately, then the recession hit. So the scale of this has not quite gotten to where perhaps the manufacturer thought it would be. The other thing that we do is we do a lot of work with houses. So I've got some detailed information about 4 research houses that we just closed out a research project on last year. These are in Oak Ridge. And how many people do we have from Anderson County? A few? Okay. So this is in the Wolf Creek subdivision. So we had 4 different methods of constructing the walls on a house, walls and roof. We instrumented these houses. We controlled these houses in such a way that we could fake occupancy. That makes it easier to compare the building when the internal effects are all the same. So we had lighting controls, we had things to fake occupancy. Yes?
I actually live really close to that house.
Yeah? Have you been inside it? Have you seen it?
No, I have not.
Okay, for a while we were giving tours. The houses are available for sale now that the research is over. We actually have several houses in West Knoxville in the Campbell Creek subdivision off North Campbell Station Road, and we have a new one off of Yarnell Road. So all of these are kind of remotely controlled houses that we have heaters and humidifiers to fake the heat load and the humidity that are brought to a space by people. And we control the lighting and we control the plug loads so that we can compare all the houses more easily and not have to worry about those variables being different between the houses. But this was done in conjunction with a builder, and these are actually somewhat standard practices, or could be standard practices in buildings. And we looked with the builder on how to incorporate these technologies or methods into houses because they wanted to have a way to offer more value to customers. It's a marketing aspect for them. And we were able to score the houses over time and compare how they would do against code constructed buildings that you might find in Anderson County or Knox County in a new subdivision, and also compare against older homes, such as, unfortunately, the one I live in is on the scale down there in the red zone. Not very efficient, 25-year-old house. My bad for getting that house. But we were able to show tremendous savings in energy use with not a whole lot of cost premium. Yes, there is a cost premium. I believe the DOE Builders Challenge, that one that's shown around the 70 value on the HERS score ranking, I think that's a 3 to 6% premium. Roderick can give information separately when we go to the cafeteria on exactly what the premiums were for these particular houses. But it's certainly doable, and it's something that people could ask for now if they had builders that were experienced in using these particular methods of construction. Yes?
Is there companies called Zebra Alliance?
That was the association between the lab and the builder, and it was the Zero Energy Building something Alliance. I don't quite remember the acronym now. The builder was Shod Construction. They were the developer. And they're based here in Knoxville. They're up on Beard and Hill, for those that are familiar with that area. The other thing we do is we do commercial buildings work. We have 2 test buildings, and again, these are buildings that we're controlling. We had these constructed specifically for our research purposes, looking at construction of 20-year-old buildings, because the vast majority of the building stock in the U.S. is existing, and it's pre-1980 construction. Really built before energy was consideration, built right around the tail end of the 70s energy crisis, not particularly efficient. So we wanted to mimic some older buildings to look at opportunities to improve them, and it turned out to be a good choice to look at retrofits, because right now the construction market is still very, I shouldn't say depressed, it's recovering. The recovery is coming very slow to the construction market, both residential and commercial, industrial, institutional. So basically we took these from concept to finished building. We did 3D building modeling. We took the 3D model and ported that into a building energy modeling software, which you're going to get to try out one type of building energy modeling software. Then we had a contractor build it, and we asked them, just build it regular. We just want a regular style building. Don't do anything special. And we instrumented it with hundreds of sensors in the walls, the floor, the roof, on the equipment. And we started measuring the data, and it turns out we wanted an old style building. The building we got was actually a lot better than we wanted, so we may actually have to go back and kind of degrade this building a little bit to get it where we needed it to be. But one of the pictures here, if you look closely, you can see one of the issues that we have to deal with in commercial buildings. On the lower right, you can see a pattern of condensation on the walls. And that kind of gives you a clue as to a problem that's unique. In commercial buildings, this is a building that has metal studs. It has metal framing, let's put it that way. It has metal girts in the walls and metal purlins on the roof. And the insulation is compressed at those points. So we have bad insulation like you have in your house, in between your studs in your house. And here, they have to hold it in place somehow, so they drape it in between the metal facing and the metal structure, and it gets compressed. So I'll show you an image of what the effect is when we have compressed insulation. You have the same problem in your house because you have the studs and the insulation is in between the studs. So at the studs, you don't have much insulation effect, unless you have a house that has exterior board insulation, which is not quite that common for older structures. So one of the things you're going to get to play with is an infrared imaging camera, and I'm going to show you some images. So this is our test building. So we've got one wall, we've got a double door, and that's a typical conduit penetration, and the lower picture there is the insulation that you're looking at. So this is the infrared camera. That's the one, I think we brought that one. You'll get to observe the results from this camera. This is like a $65,000 camera, so I won't be handing it around. Because we're still accountable for getting it back to the lab in working condition. A lot of building companies, building energy auditors, they use IR cameras. You can get them for about $2,000 now. You don't have to get a research grade camera. And Mahabir took these photographs for me. He took the images. So our same building, that same end of the building, in the top image you can see exactly where the girts are in the building. So that's where the steel structure is, and that's where that insulation is draped over there, and you have a continuous line of thermal bridging there. We don't have enough insulation. This camera is sensitive enough that it'll pick up the screw holes. So it shows the leaks exactly where the metal exterior is screwed on. We also took a look at the doors and penetrations all around the building, so we know exactly where we have problems, and in about 2 weeks we're going to go back and we're going to seal up all these and do it all over again. The bad thing about this is to get a really good image, you've got to do it with at least a 20-degree temperature differential, and preferably when it's dark outside. So these images were taken at about 5:30 in the morning when it was 25 degrees outside. I'm not looking forward to doing this again, but we got to do it when it's dark, and it's easier to do it in the winter. It stays dark a little longer for us. So basically, what we work in our group is we want to find solutions that we can help industry get to the public, that can get out to the market. It's not enough to just discover the material. We've got to get it to where people can use it, and they can use a lot of it across the whole country. Or even for some manufacturers, there's a global application to this. So we try to work with people early on, and this slide shows for a new company or a new product, that progression. At the very beginning, you're not selling any product. You're not making any money. You're just spending. You're in the hole. You're digging a deeper and deeper hole through research and development. And we work with people during these first 4 stages: research, development, demonstration. That can be what we do on our test buildings. It can also be what we do in our test apparatus, on our large-scale apparatus. Deployment is more, that can be more of deploying to select controlled test sites outside of our area. And then commercialization is when they bring it to market. Hopefully we get something that's a success, which on the revenue stream it shows that they're making money, because they all want to make a profit. Hopefully they make some profit. Moderate success is still success. A lot of times though, it's a flash in the pan. We have something that looks good and promising, and then for some reason or another they just can't sell enough of it, so that's the end of that product. And some just never get off the ground. Some can't be commercialized. They look promising, but for some reason or another, perhaps it's a material that's too expensive, or it's a manufacturing process that's just too complex and we can't figure out how to make it more simple. It's down there where it never makes any money at all. Unfortunately, that's categorized as dismal failure. So we don't like to claim that we were involved in any dismal failures, but I think the first go around with the water heater 20 years ago, that probably would be in the failure mode. They did sell some for a while, and they did make some money for a little while. Anyway, so what we're going to do next, we're going to go in the cafeteria, and we've got several stations set up. So let me describe, and my UT helpers are about to dispatch to get in there ahead of you all. We don't need everybody congregating around the IR camera all at once. So what we're going to do is we're going to take probably 10 people for a different station. We've got about 5 different stations. And then we've got about 20 laptops set up where people can share laptops, maybe about 2 people per laptop. And Dr. Mahabir Bhandari is going to go through the modeling process. So most of the stuff that we're going to look at today is things that you can see in your house. We didn't talk about commercial or industrial applications so much, but all of our examples are things that you probably would be familiar with in wherever you live right now. So before we go that way, does anybody have any questions about materials or air conditioning, water heating, how to cut your electric bill for mom and dad, anything like that? Yeah.
I mean, I notice I have drafts in my house, and I don't have an infrared camera. So what's the easiest way for me as just a simple homeowner with very few resources to find out where that air is leaking in?
There's 2 different ways to go about it. One is just to assume the worst and apply some of these low-cost applications everywhere, like putting these little insulation pieces on receptacles. Because I know all of my receptacles leak in my house on the exterior walls. Just going ahead, unscrewing them and putting them all in there. The other thing you can do is it is possible to buy an inexpensive smoke pen that's non-toxic, that shouldn't leave marks on anything, and you can actually squeeze the smoke pen around places and look for air movement there. We find it's really hard to find air leaks. Even with our IR camera, we did it on our test building. We wanted to find leakage, and it wasn't enough, even though it's a really expensive, high sensitivity camera. We did blower door testing, and we know how much the building leaks, so now we've got to go back in about 2 weeks and just take a caulk gun and go back and hit all of the usual suspect places. Any kind of a penetration, electrical receptacles on the outside of the house, there's foam spray that you can put in there. Ceiling lights at attics are another big candidate. Ductwork penetrations usually have almost no ceiling around them, and if they're in your second floor, they communicate directly to your attic. Doors and windows. I'm good with the doors in my house. My windows are terrible. I haven't touched my windows in my own house. We have 2 people that are really good in that area that you can talk with that can give you lots of details for your specific case. Yes.
What I did for my house, I was able to reduce my energy significantly. The low cost thing, I just took a lighter, one of those ones with the stick on the end that you can curve around, and went around the edges of my house, and wherever the light, wherever it flickered, I could tell that there was air coming through, and that's where I applied the most of the caulking and stuff that she's talking about. And I was able, when I lived in Kingsport, and I had a house built in the 1920s, and I was able to reduce my energy bill by about $50, same temperatures, you know, from one month to another, just by doing that. So you have to be careful, obviously.
Yes. Yes, no one under 18 do this.
Yeah, you don't want kids to do it, but as adults, you know, if you want to go around and test with something that'll move when the air is coming through. Really low cost.
Like the smoke gun?
Yeah, the other thing, some people like to use incense sticks for that purpose.
Yeah,
I can't stand the smell of it, so I wouldn't do it.
Something you can detect air movement with.
Yeah, but you can, it's estimated that most people are wasting about 30% of their utility bill on leaks alone. So, and it's low cost, it's not glamorous, and you don't need a contractor necessarily to do that. You can do it yourself.
Foam things that you can put around if you take off the covers
Yeah.
of your electrical stuff and put the foam things
Yeah.
underneath, those work well
Yeah.
too.
Yeah, and TVA has a kit that if you get online, you can get a little kit and they'll give you some samples of those and a light bulb and a low flow aerator to go with that. Yes, what's your question?
Go ahead.
How would you stop air from going through nails and the walls and ceiling and stuff? How would you stop them from letting out air and money and all that stuff? How would you stop it?
Well, now most buildings, the sheathing that they have has a surface on the outside that's somewhat of a self-sealing process. That after it's nailed in, it tends to seal around the nail by itself. In the case of my building that I showed you, the screws, there's not a really good solution to that building where those screw patterns are visible. We have a bigger issue, which is that we've got 5 inches of insulation behind there that at that point is compressed to about 2 inches. So we're going to go after the insulation, and we have a facing on the inside in that case that's going to stop the air. So we don't have to worry about the individual screws that much, thankfully.
So you block the other side.
Yeah. Yeah. Yes.
Right there on the doors, I'm pretty sure the doors it's because there's cracks in the doors and that's why it's blue because air's coming in.
Yes, absolutely. We're going to go back in about 2 weeks and we'll have a before and after picture on that. So you're correct about that. Any other questions? Yes.
You mentioned that your house is appropriate is about a 5% improvement. Is the marketplace ready to pay that back? What's the payback? I mean, if you take a $200,000 house,
The paybacks are long on envelope improvements. However, your envelope is going to last longer than your HVAC equipment. You know, your HVAC equipment now, if you're lucky, you'll get 12 to 15 years out of it. But your envelope, you're kind of stuck with it. You know, unless the exception being roofs. We all know that roofs have to be replaced periodically, but your walls, not so much. It's a one-time deal. You know, paybacks can be 7 to 10 years. So certainly if you are invested in the stock market and you see a better opportunity, you've got to evaluate where you put your money in that case. It makes envelope improvements a really hard sell, really. I know in my case, I need to replace a whole lot of windows in my house. That's a really expensive envelope improvement. Functionally, there's really no payback to going to a more exotic window than what we've already got in our house. So, you know, that's too bad, but without payback, there's no incentive to do that. The exception would be a rebate situation, and right now, I believe those rebates are no longer applicable. Those federal rebates that we had for windows for a while, and even equipment. You know, we had some pretty good equipment incentives. It depends on where you are in the country too. Parts of California and places like that, they have other incentive programs. Even like Maryland incentivizes heat pumps, ground source heat pumps. That we don't see those opportunities here because we really only see the federal incentives. Yeah. So there's 2 or 3 people that deal with envelope type retrofits that can speak to exactly what the paybacks were for those particular houses. And that 3 to 6% builder's premium, that was for a DOE Builder's Challenge home. Actually, the premiums on the test houses were a little bit more than that. Yeah. Yeah. Yes, sir.
Does the lab get any return from transfer technology?
We can if we.
Is it the case now for the Zebra Alliance partnership that you have with them?
In that case, I don't believe there's any intellectual property where there would be a technology transfer in that sense of a tech transfer to an industry. But we do have cooperative research and development agreements with HVAC equipment manufacturers, such as that for the water heater, the heat pump water heater is an example. And also we have a new, we worked with a company to develop a new ground source heat pump system that was an R&D 100 award winner, and that would count as tech transfer in that sense. Yeah. So we see a lot more of that on the equipment side just right now, but it could be envelope as well. Someone else have a question?
Will you go back and tell us one or two or three agencies that help do consulting for energy efficiency, or the TVA have a program?
TVA has an energy audit program. Basically, I can't remember what the cost arrangements are. They will have someone come out and do an energy audit, and then if you choose to implement the recommendations, there's a rebate that will, I believe, cover the cost of the audit plus some. I'm not certain. There's a couple of people here that have experience with that program. I haven't done it on my house in particular. Another option, we have some handouts also that are from DOE that are about home energy that we'll give you today. The other thing is to go to energy.gov and look at their literature about home retrofits and home energy assessments. And also the EPA, through their Energy Star program, has a section dedicated to residential applications and the same kind of assessments and retrofits. So all that literature and recommendations on how to find contractors and assessment providers, that's all available for free, in addition to what TBI offers as well. Yeah. Yes?
Couldn't you use solar energy to power your air conditioner?
Yes, it is being done. The problem is the size of the solar array that you need in order to drive an air conditioner of a sufficient size for a house that we're accustomed to here. We are getting ready to do an assessment for a DC powered air conditioner that's about 12,000 BTUs, or one nominal ton of cooling, that is strictly powered off solar. And we're actually doing that. We're doing work with the Department of Defense for expeditionary energy at forward operating bases, such as what's in Afghanistan and also in the Pacific region. And we're looking at really aggressive low energy use air conditioning for tropical and high heat climates that can be powered off of alternative energy sources. And we are looking at solar systems that are linked with batteries to get off of generators in that case. But in that case, the cost of energy is about 4 times higher than what we see here. So there's a definite financial incentive to go that route. Yes?
But while you're in the tropics, isn't it better? Don't solar panels are better in colder climates?
Your solar depends on where you are in relation to your position relative to the equator, basically, and your ability to capture solar rays. One of the challenges with being in the tropics is if it's a tropical situation where it rains a lot, you're going to lose solar opportunity. So that just drives your battery array larger. So it's a cost, it's a weight, a size issue. Certainly it would work great in the desert, and they are using that in the desert. Yes?
Is there an impact to the environment when we're doing all this testing to find new materials and things like that? Like I know, for instance, when they started to add like more tablets and things to, there's like lots of rare earth metals that they had to dig up and stuff like that. Are you seeing the same kind of thing as they try to add these new materials that aren't just wood, or?
We have a lot of different material issues. There's the embodied energy to develop the material. There's the environmental impact of the material itself immediately when it's applied either to the installer or to the occupant. Formaldehyde is a big issue, is an example of that. Certainly asbestos is another great insulator, terrible material health-wise. I think people are so sensitive to that now that we look at it early on the front end, and we kind of weed those things out early on. One thing that's going to come to the forefront later, though, is, well, it's starting to come up now, is what's the environmental impact of disposing of a building? And certain materials are going to be nearly impossible to recycle, so that's a problem. So, okay, well, with that, I think we need to move on to our demonstration. So we have our helpers ready to hand out your data collection sheets, and we'll just try to divide up groups to get manageable sizes at each one of our stations. Okay? Thanks.